Okay, this is going to be an overview lecture on dynamics Newton second. So when I say the overview, I mean to say it will help you go through the course, but it won't be, you still need to attend the lectures and all that. So it's just helping, supplementing, if I would say. So first semester or first year, they should have talked about something called statics, right? Statistics, from high school, it kind of looks like something's not moving, but I wanted to say maybe for statistics, forces are in balance, right? Okay, you can say body at rest because it feels better if you say that, right? And now we're moving to dynamics, right? The one that we're trying to discuss today. Now, forces not balance, right? So what are we expecting? Motion. So I think that's how you see this guy Newton here, because most of his definition, first, second, and all that, they call them Newton laws. They were very, motion related if you're trying to talk about them. So if you write it, look like this. So it was saying that when a net force is exerted on an object, when a net force is on an object exerted on an object will accelerate in the direction of a net force with an acceleration in a direction of what did I say? Let me start over. When a net force is exerted on an object will accelerate in the direction of net force. Also, that acceleration will be inversely proportional to the mass and directly proportional to the force. Yeah, I might not say it by like the book, but you get the point what I was trying to say here, right? But for now, since you've been seeing a lot of stuff you don't know, I think now you can see that now this acceleration is just a second differential, right, of position. Oh, it's better if I just do double dot. Remember, you know that if you have, let me call it r, if you have r and you differentiated dt it r, you get double r dot, of which is just velocity. And if you do that again, forgive me for using this wrong notation, you'd end up having acceleration. So acceleration, technically I'm trying to say acceleration, you differentiate, go to velocity, you differentiate, go to acceleration. So that for you, it should actually tell you, oh, the other way around, I'll be integrating, right? So that's actually alone covers the whole chapter, but we're still going to go in and see if what more we can say about it. Okay, in terms of forces, there are a lot of forces. One of the force types, let me say classes, I want to say classes, that feels better. One is when the force is constant, maybe the one that you've been seeing mostly in high school, constant, right? So here the force is the same that is applied. We've been using this in basic kinematics, and here it will yield out a uniform acceleration, right? And another force that you could get time dependent. Let me say time dependent. So here the force was the same. Maybe it was, let me say, 5 Newton, like the one that you did in high school. There was a box, maybe there was 5 Newton here, so that was a constant one. Now you can also get a time dependent. So a force itself is a function of time, so maybe with time the force is changing, right? A lot of examples that you can think of that are like this, but I'll let that be your problem to worry what other forces you think could be time dependent. If you have an idea, I think it's the right time to just write a comment and say maybe this is what you think are time dependent. But as the course continues, we'll see. Okay, 3, let me call them velocity dependent. These ones are forces that depend on velocity. So this one, I like to share it with you because it's not so common. I think these ones you can make them up or you can think of ideas. Friction. Friction is one of them, right? And drag and all that. Because you remember in high school you talked about static and kinetic friction. They're literally showing you that friction actually depends if the object is moving or not moving. So what is a force that's actually dependent on velocity? So yes, we have velocity dependent. Let me say on 4 we have position dependent. So position dependent, it could be a spring, an oscillating spring with some mass. So you know that a spring, like how much force it gives you depends on how much you have pushed it or the position of it. Also, I think I don't know if this applies very well. This is a height, because other people normally put 5 here and have something called gravity alone. I don't want to put gravity because gravity, you know, mgh, you remember? So it was mainly depending on height, and height is the position. So this guy for me looks like he belongs here. So if this thing was here, it would be the force that is feeling will be different, the force that you're feeling will be different depending on its height. Let me say height 1, height 2. So now you know that there's a time dependent force, there is velocity dependent force, and there is position dependent force. So remember, the goal of this chapter alone is you being able to find RT. You'll be solving for RT. So what are you having? You're having a whole differential equations, and you're trying to go back to finding the position vector, if I should say. So if I could give you steps so that you have an idea, this is a step that you'll be doing almost in every example, but it might look different. First of all, it will be writing Newton second, right? Please note this one. Second one will be identifying forces, force expression, right? 3, you'll have to formulate the DE. DE is differential equations. 5, you'll have to integrate first time. You remember integrating first time will give you what? A velocity. That was my 4th. My 5th, you'll have to integrate again second time. That one will give you what? This was velocity. This one will give you position. I'll use R for my position. Then number 6, hopefully it will become, you'll have to apply initial theorem, or you'll have to apply IVTs. Like I will give you maybe a time 0, it was this, so you have to just plug those and remove the constant. Remember, if you integrate you get a constant, and these ones will help you get rid of the constant. Step number 6. So whenever we're doing this problem, I want you to in your head say step 1, step 2, step 3, so you have an idea what we're actually doing. Alright, then you have to interpret the motion. This one is very important actually. Let me put it in black. Number 7. Right, number 7, I want you to be able to interpret. When I say interpret, at least you should have an English, pure English, not serious English, just an English that I expect an engineer to write. Just say, how is the motion going on, right? So yeah, that's all that we'll be doing here for Newton. And let me start with a very easy example. Let me call it example 1. Example 1, let's have, obviously you know what teachers do, that they bring an easy example, then in the test they bring way harder ones. So let me do an example where a block is pulled. I'm so you're angry now because this is what you did in high school. So this is going to be my first example in dynamics. Okay, a problem is saying let me say a problem is saying that you have a 2 kg block and it's pulled, I'm making it up, I hope it works, it's pulled at 10 newtons, pulled by 10 newtons on a frictionless floor. When I say frictionless, I'm trying to say avoid Fk or Fs, give them 0, and then I want you to find Vt and some position function, right? Okay, cool. If, let me give you an condition. If initially it's at rest, right? So you know that at time v at time 0 is equals to 0. That's what our initial value they gave us from just saying that. Please, from here now, please copy this, pause the video and try if you can give me this guy and this guy on your own, right? Okay, remember the steps, right? Step 1, let me see what step 1 said. Write Newton's second, right? I want you to think of it like this. You're not going to cheat and go back because this thing could be, you can even do the other step, but it's going to help you figure out what's going on. Newton says that F is equals to ma, right? But we know that F is equals to m x, let me say in this case x dot dot. Okay, someone will be like, no, should be actually be F d t squared. So it's a second differential, so it's same method depending how you want to write it. Okay, cool. So did I give you, then what's the next step? That was you writing Newton. Did I give you stuff like your mass? I made up a mass of 2 kg. So from here, F is equals to, we know the mass is 2 kg, but you know d x squared dt squared t is equals to that. Force, did I give you? It's a constant force of 10 newtons. So from here, obviously you can do what, you can divide by 2, you'll have 5 is equals to dx squared all over d squared t. This is like differentiating twice, right? So now it's look nice like this. Now you have a differential equation. So let's see how much steps that we did that, and we already formulated a dE. Now we were supposed to do differentiate for the first time and get v. So if we differentiate now, we'll obviously get this answer, right? So if I differentiate here both sides, I have a 5 here being integrated, and then this side is obviously dt is equals to this side. Let me write this one like this, is d dt, and then inside I'll have d dt of x, right? And I'm trying to integrate that in terms of t. So by now that you know that's an integration and do differentials, someone have told you that in your life already. So this guy will get rid of that guy. Oh, let me just say it the right way. This integral, you see, is going to get rid of this differential, right? So someone would like to think of it like this cancel that guy. Now you have a d summing all. Remember, d is a very small thing. So if I can sum up all the small thing, I'll have one whole thing. So you technically have a 1. You get rid of all these things and have a 1. That's how other people prefer thinking about it. So now this side you have d dt of x. This side, if what happens if you differentiate as a constant, I don't know what happens. Okay, pause there. I think you know we're supposed to think and comment also and tell them what do you think happens when you differentiate. But I think you took calculus, you'll get 5t, the constant that was there need to come in, 5t so 5t plus c. The reason why here someone will be like, if I integrate this and I'm supposed to get a constant, let me call it that constant plus c1. So technically that c1 you can put it if you want, but if you take it this side, you'll have c2, let me call this one c2 and c1. You'll end up having 2 c's and they still equals to c if you sum them. So a constant by a constant plus a constant become another constant, so it really doesn't matter so much. So it becomes big C then, right? And we know that if you differentiate a position vector, you get velocity. So from here, this is just velocity. So already now we know that v of t is, please note of my v, it doesn't look nice, is going to be 5t plus c. So we could get marks here, but now we don't know what is c. That put us in a very bad position. So yeah, so that means we need to do it again until we can use initial. Oh, they actually did tell us initial value set at rest. I mean, initially this thing was at rest. So at time 0, so we know that this was 0 at time equals to 0. Now we can try to solve for c. This guy will disappear, this guy will disappear, and c will end up being 0. So c really doesn't matter. Can get rid of it. So how I got rid of c. Please, if it's something you are not getting clear, please go back to the video and try to just go back and see and listen to it again. Hopefully it'll get better. And also, if you feel like you don't understand something, just leave a comment or something. I'll maybe go a video where I'm trying to brush up what I feel like, or you feel like I didn't do justice. So this video, please forgive me if it's getting too slow. I'm trying to make sure that all the basics are very synced with you, so that if you continue with other concepts, you already have these ones easy. Okay, right? You know that remember our map there? If I'm at where was that map? Writing. If I'm at V and I'm trying to go to R or position, I will have to integrate. Remember, integrate is the blue one. Right, let's go back here. Now let's integrate both sides. Right, remember this guy is same as d dt of r or of x, depending what you're talking about. Okay, so obviously if I integrate on my left hand side, I'll just yield out x as it is without anything else, right? So here it will become just x of t. That's what we've been looking for. And this side, this guy will get a 2, then I'll divide by 2, then I'll have a 5 all over 2t, then I'll get another constant, and we call it k for now. Now this is we have answered the second part of the question. Also here we could take advantage of, we know that at time 0, before this thing moves, it had 0 displacement. So before this thing move at no time, if I want to put it like that, at time naught, right, this thing didn't have displacement. That's a nice way of writing what I just said. So technically we go there at time naught, this thing didn't have displacement, right? So whatever this thing is was nothing in the beginning, right? It's giving kinesis plus k. So now this thing was time naught, so time naught squared and everything naught, it doesn't matter, and our k become naught again. So lucky enough, we've solved this part. All right, so this is our position, and I think we did v somewhere, I don't know, let's try to find it. I don't know where we did v. Oh, v was just here, just didn't write it explicitly. So v is going to equals to 5t, because the constant was also 0, right? So also remember there was the last part where I said being able to interpret the motion. The part of interpreting the motion, you just look at this guy. So from now you can see that this thing will be it will be a parabolic motion in time. So as time changes, this thing traces out some parabolic function. So please check out more videos that I'll post. We'll look at gravity, velocity. We'll solve one example for each of these things, then I'll start giving more tutorial questions on it. It's as simple as this. Please go back, check the video if something you missed. Thank you for watching.